Yeah, this section is about, well, I guess integration with smart grids and power applications. And I'm going to talk about two different aspects. One being our what we've called a smart grid demonstrator, which tries to figure out how we might interact with different kinds of networks. And then we've got another case study which relates to an interconnector between Scotland and Northern Ireland, which is another kind of waste or excess heat source is utilised in a power generation application. The first thing is that there's a video now, and hopefully that'll start as soon as I click here. This one's on YouTube, so you should be able to find it through the H-DisNet website.
The H-DisNet Thermochemical Smart Grid Network Demonstrator has recently been established at the Sir Joseph Swan Centre for Energy Research at Newcastle University. The demonstrator aims to determine how a thermal-chemical network can distribute and use intermittent and low-grade thermal energy. A thermochemical network will be constructed from a network of uninsulated PET pipes. Some will carry a weak liquid desiccant water mixture, shown here in grey. In parallel, a supporting network will carry a strong liquid desiccant water mixture, here shown in green. An energy source, in this case a hot exhaust vent from a bakery, will be used to recover the liquid desiccant. Using an evaporator unit, the weak fluid is heated at relatively low temperatures. In this example, at 60 degrees Celsius. Some of the water carried in the fluid will evaporate, leaving a stronger liquid desiccant water mixture. A network of energy sources can be developed that includes excess heat from industrial sources, solar thermal, district heating systems, electrical transformers, etc. Unlike conventional heat networks, the energy is not stored in the form of increased temperature, which can be lost with time. Instead, it is stored in the strength of the desiccant water mixture, or its thermal chemical potential. As such, network pipes don't need insulation, and the desiccant water mixture can be stored in uninsulated large tanks for later use. The strong liquid desiccant mixture can then be pumped to energy users for air drying, heating, or cooling services. The dehumidification of air to facilitate industrial drying is the simplest application. Here, the strong desiccant water mixture is used together with a dehumidifier unit to dry air for a local indoor swimming pool. The combination of dry air and an evaporative cooler can be used to support air conditioning for the cooling of local buildings and greenhouses. Furthermore, the dehumidification process can be exploited to offer a mild heating and air reconditioning services for local buildings. The H-DisNet system aims to be the first demonstration of a multi-node smart thermochemical network. Within the laboratory, multiple energy sources have been installed, including a combined heat and power unit and a thermophotovoltaic heating system. In addition, a highly controlled electrical heating system has been developed, which can emulate the day-to-day and hour-to-hour thermal outputs of real-world excess heat supplied. A smart thermochemical network comprised of an advanced control system and embedded thermochemical storage is then used to supply energy to different end users.
Right, so that's the end of the video. Marco, can you give me control again of the slides? I've got some slides to sort of summarize some of those aspects.
Yes, I'm on it. You should have control now. Yeah.
So thank you, Mark. So thank you. So as mentioned in the video, and as mentioned kind of a number of times across this webinar, we've had a number of there are a number of places and different ways that actually H-DisNet technology can be applied. It can be utilized across different energy sources and different energy demands. There's some kind of open questions around that. How do you match energy supply and how do you match energy demand? So the next natural question is, how big does storage need to be in order to move energy and keep it within that energy system? And then these different technology sets and sources and sinks of energy, they need to be coupled together. How do they work together? Do they complement each other, and so on? And then final question is really, how does that system, once it's been established, how can that be controlled in a way which means that you don't have any failure of any energy services? So what we wanted to do with our demonstrator was to try to do this by building what is, you can see there, an apparatus there that's been designed and built to be self-contained, so we can test different aspects of those challenges. So we've built this, what we've called a flexible test platform, and what we can do within it is test and create the conditions of multiple thermal energy sources from up to 90 degrees C, and we've also kind of gone the other way, all the way down. I think the lowest we've done is about 30 degrees. Within that system, we can emulate different thermal and air conditioning loads. And within it, we can also store the heat as heat, or we can store it within the thermochemical fluid itself for recovery when we need it or when we want to use it. And we've got embedded within that a number of control systems, and we can measure every aspect of what's going on within the system to measure the performance. And then we can use that to then try out different alternative ways of controlling and testing the system in different ways. Across the apparatus, we've been characterizing some of the components. So we've characterized some PVT systems, that's the thermal aspect added into photovoltaics, thermal collectors, the use of electrical heaters to power the system, and we've been characterizing the inputs, the outputs of those different components and measuring efficiencies. We've also instrumented up our network, as you can see from that complex diagram there in the corner, to measure the different key flow rates, the gas flow rates and so on, so we can measure exactly how well the thing is operating. And we can obviously characterize the temperatures and concentrations and humidity and all of the energy usage across the system. I'll move on to the next slide. Oh, I need to go back one now. Turn back. So our initial testing was what I called two-node network testing. So this would be a source and a sink. And in this case, we were looking at renewable energy to air conditioning demonstration. So we used our PVT system, and we characterized the PVT system for, what was a North UK temperatures, solar irradiance. And we found we could recover from that system about 50 degrees of heat. Obviously, that varies depending on where you are. And we could then use that fluctuating solar energy to then produce local cooling via the H-DisNet technology, 4-degree reduction and a 10% relative humidity in order to sort of demonstrate that we can do some local air conditioning. And we've been measuring that and trying to characterize that system. The next example that we've been working on has been slightly more complex. I would say that this is a 3.5 to 4 node system. where we've been using that PVT system with its intermittency, and also using electricity to heat the fluid at key times of the day, using what we would just sort of loosely call excess electricity. So off-peak electricity would be used to do heating, and then we can then store the recovered desiccant fluid in storage and then use that in a time-shifted way to produce, and in our case, we were looking again at air conditioning. And then the final scenario we've been looking at is emulating excess heat from industry and the return line from a district heating system, and coupling those somewhat more regular profiles into storage, and then looking at how we could time shift that to deliver what people wanted as air conditioning, heating or drying, but using demand profiles from different cities across Europe. And I think, from memory, we can just summarize what our demonstrator does. So we've developed a flexible test platform at Newcastle. We can try out different configurations of networks within our test platform, and we were exploring different energy sources and demands to emulate and control them in an effective way. Then next, I'll give a quick summary of what we've done across our work on the Moyle interconnector system. I don't know how many people know much about interconnectors, but an interconnector is an electrical system, and it transfers large amounts of electrical energy across long distances. So a good example here, one of the first ones is what our case study is on, and it's the connection between Scotland and Northern Ireland. And this connection basically takes the AC current seen on either side of that line, and across the sea, it's transferred as direct current. So you have a process where you convert AC to DC. You then transfer that electricity under the sea, effectively on a cable, and then you turn it back to AC on the other side. What's interesting about these connectors is that as we have more and more offshore renewables and we're transferring energy more and more often across the planet, these sorts of systems are becoming very, very, very common. And this system at the time, which was a 500 megawatt system, was one of the smallest. And now it's very small compared to some of the other ones that are going up across the world. But the key thing is that the system is almost identical everywhere you go. And about 1% of the energy is lost in the transfer process, and almost all of that goes to low-grade heat. So whilst the losses to heat are very small, the actual, in terms of percentage terms, they're actually enormous in terms of real-world numbers. So this system is a 500 megawatt system, so there's 500 megawatt system. So 5 megawatts is actually vented heat to atmosphere at around about 40 degrees, that kind of scale. So the question for us in this work was whether or not that energy could be utilized in a more effective way. When you break down the way a system works, the losses are mainly across the transformer and the thyristor valves within the system. And that's where we focused our work. So what you have within the center is you have a stack of thyristors, and they're held within a room, and that room is air conditioned to 15 degrees centigrade, and to keep the humidity as low as possible. The reason to keep humidity low, and the reason why it's air conditioned, is to prevent corona discharges from one side of the thyristor set to the other side. So what we have to do is we have to maintain, we have to take external air, which is you see a different concentrations of, different humidities and temperatures across the year, and you have to maintain that at 15 degrees within the system. So there's an air conditioning system which delivers that. There's an excess heat sources within the interconnector, as I mentioned before. One source is actually the cooling system for the thyristors. So water is pumped around this thyristor cooling set, and around, well, about 400 kilowatts per side. So there's two sides, so there's double that. So about 800 kilowatts in total is available at about 40 degrees centigrade. So that's recoverable heat. And then the second source is across the transformer system. There's a cooling system which cools down the transformer, and that again is in between 300 and 378 kilowatts of heat per pole, slightly higher temperature. Obviously, again, a very, very high efficiency process in electrical terms, but actually when you strip it back and you do it at a large enough scale, there's a lot of heat being generated there that can be utilized. And the idea was that we used the heat to drive the desiccant system, and the desiccant system would be then used to offset the air conditioning requirement for the thyristor hall. The calculation was made more complex because the demand on the site, the utilization of the connector varies in direction over the different years and seasons. But the key is that weather also affects it as well. So we collected data over a number of years and analyzed the amount of available heat from the system and worked out, actually, is this going to save money for the system? We looked at what we call the case study, which was a retrofit, which was basically just fitting H-DisNet installation around the existing infrastructure. And we also looked at two scenarios of what we're calling new projects, which had slightly different ways of implementing the system, and worked out the payback time for the technology. So the payback times here varied from about 8.7 down to 5 years, and they were all using the savings in electricity in order to justify the payback period. We also looked at other energy recovery technologies from the site in order to verify and see how effective the solution was compared to things like the organic ranking cycle, etc. But we found that this was actually the most promising in terms of actually delivering something that was actually useful. That's mainly around the fact that utilization temperatures are much lower, and things like organic ranking cycles and other heat recovery systems are not that cost effective at these low temperatures. If you'd like to find out a bit more about this particular piece of work, it's been published in Applied Energy, and the reference is down there at the bottom. It's a much more comprehensive description of what I've just said. And I should now say there's a few more minutes for questions before we move on to the next section.